So we're going to start the student session now. I didn't know I was actually introducing the student section overall, but these are student presentations that are in the context of Unix that are going to sort of show us the next generation of where these things are actually going. And it's my pleasure to actually bring up Jimmy Lin. He's from, please come on up. Thanks. He's from Margot Seltzer's group from the University of British Columbia. And what he's going to talk to us about is how we can actually use some of the understanding and ideas of Unix to actually understand machine learning and actually drive our forward thinking. So please, Jimmy.
Thank you, Chris. Hi, everyone. So I am Jimmy Lin, and I'm from University of British Columbia in Canada. So I want to talk about how we can take some of the philosophy of Unix and help it improve the direction that machine learning is going. So today I want to talk about the theme of simplicity and how the Unix pipe helped drive that into the Unix system overall. So one thing I like about how the pipe works is it takes two different programs and pipelines them such that one is only communicating with the pipe interface and doesn't actually know what's on the other side. And I think that this is a really nice way to think about problems and actually has been critical in helping me design some better algorithms for how to train machine learning models. And just in general, I think the idea of simplicity and modularity is something that we can help machine learning with by introducing it into how we think about the problem. So let's start by thinking about what is machine learning. So in machine learning, what we try to do is we take some kind of world, usually it might be like a game, or maybe like a real-world problem, and we want to build some kind of model of understanding of how the internal dynamics of that system works. And the hope is that we can build something simple enough that we can understand it and reason about it, so that when we see new instances of things happening in the world, we can reach back to our model, consult it, and see what kind of decision it recommends to us. But over the past 10 years, we've reached a bit of a problem with machine learning in that our models are actually getting quite complicated. And to the point where sometimes it's starting to get just as complicated as the original problem that we're trying to solve, so we don't really gain a sense of understanding, and we're kind of being left behind by the models that we produce. And while sometimes this might be okay, because in some cases where the risk of what we're using the model for might be pretty low, there are also scenarios where we might want to actually understand what the model is doing. For a couple of reasons. While the model is trained on data, and the data might contain some flaws or biases that we might want to account for. If we can't understand what the model is doing, we can't really know how the biases might have influenced those models. And if we want to actually correct them, we might not be able to reliably fix them without introducing other artifacts. So some of the important decisions that we're using machine learning for, or starting to look into, are credit risk assessment, parole decisions, and hiring recommendations. Now, these are decisions that actually impact a person's lives. So we want to make sure that when we deploy some kind of model that's going to impact those decisions, we understand what's going on. We know the limits of when this might work, when this might not, and what are the risks of failure within that model. And further, if we can understand it, we might be able to even begin to try and correct some of those problems. So with that in mind, why don't we build more simpler models? Well, the issue is that a lot of times when we try to train the models, what we see is that as we try to increase the accuracy of a model, the simplicity of that model starts to get lower and lower and lower. So I'm going to coin this term the price of simplicity. So this is the price and accuracy we pay if we were to decrease or increase the simplicity or interpretability of that model. However, this is mainly a belief that we have based on the models that we've seen so far. The issue is we're actually using algorithms that don't guarantee that the model coming out of it has any kind of optimality. So what that means, we're not entirely sure if there's actually no models here. So we could be doing better, but we're not sure about it. So suppose there were points over here. We could see that we could plot a line over in that direction and see a more, I guess, a lower cost of what we need to sacrifice in interpretability in order to keep our highly accurate models. So now that raises a different question. Why don't we just do that? Right? Well, there's no such thing as a free lunch, and unfortunately, the algorithms that guarantee optimality in an optimization problem often are a lot more expensive. So that means the reason why one might not want to run the algorithm to train and get these better models that are both accurate and interpretable is that they're often quite slow. So we can actually relabel this chart to see this is actually just the price of me not wanting to wait. And this disparity in accuracy is just because I don't want to wait for too long for my algorithm. So knowing that there's two paths forward. One path is, well, I can wait. And the other path forward is, well, we can look at the optimization algorithms we're using and see if there's possible ways we can make them faster. And hopefully, if we make them fast enough, the difference in time needed to reach optimality would be trivial enough that it wouldn't really make sense for us to still use our greedy algorithms. And that's the area that I'm working on. I'm trying to close that gap so that we can reach these models without having to wait too much longer than, say, some of these. So I want to go back to the idea of the Unix pipe and how that can actually help us design better algorithms. So one way to think about a decision tree model in machine learning is to actually reframe it as essentially a pipeline of data. So when I use a decision tree, I put in some kind of data, and then it asks a bunch of binary questions about how that might work, or how the observation of that data is, and it comes out with a prediction of, say, if I have some data set about animals, it might guess some of those are cats, some of those are bears. But we can reframe that process into a pipeline of smaller programs. So a decision tree essentially would just take the data set over here, and we run a small program that separates that data set into small animals and big animals. So then we can either from there recursively separate the data set more, or once we've reached some level of confidence about what that subset of data is, we can just predict it. So for example, you'll notice the labels up here are all smaller animals, and the labels down here are all big animals. Now, something pretty magical happens here when we start to decouple the model using the Unix philosophy of keeping things simple and keeping things modular. And that, remember when I talked about how one program on one side of the pipe is oblivious to the other, what's happening on the other side of the pipe? Well, we see the same pattern here in that the program running, or I guess the small little separation program here, has no idea what's happening over here. All it sees is the data coming out of the pipes. So what that means is the optimal model, no matter what it is, if it at some point has this set of data, we know that we just need to run this program behind it and all the other programs behind it as a pipeline, and it will reach the best predictors possible for this subset of data. So we can actually reuse some of the work in our optimization when we try to pick the best programs that will eventually compose into our best decision tree. And so I have a visual representation of what that looks like. So here we have the same data set about animals, but we start off the pipeline two different ways because we're not sure which one is the best. Now, either way, we can either partition the data about using the animal's size, or we can partition the data using the animal's weight. And in some cases, we end up with features that are so similar that the resulting subset of data can repeat itself. So it might happen that the small animals go up here, the big animals go up here, but it happens that the big animals are also the heavy ones. So we have the same data set repeating itself, and then the lighter animals are down here. So what that means is once we reach the optimal model that is needed to predict this set of data, we don't need to redo that work again. And this kind of modular thinking allows us to improve our algorithm by not reproducing the same work over and over again. And by doing that, we're able to reach a speed up of roughly a factor of 4. And that's the kind of performance boost we can get when applying the Unix philosophy to machine learning training. So what's the takeaway message today? Well, for one, we've been settling for more complicated models even though we don't really have to. But the price is we have to either come up with better algorithms or just be more patient about the training process. And additionally, we can overcome some of the cost of having to wait for better models by actually working on improving the training algorithm of machine learning. And we can do that by actually using some of the philosophies that we have applied to help the Linux system develop to what it is today. And with that, I end my presentation.
So today we're going to introduce you to Michael Hahn, who is a fourth-year PhD student at Harvard University. I asked him, is there something interesting that you want to say about him? And he said, he's very boring. But if I look at his topic, he's trying to solve real problems in security, privacy, and machine learning. It couldn't be a boring life if you're going to try to solve those problems and look at data provenance. So let me introduce you to Michael Hahn. He's going to show how his work also connects to the Unix philosophy. Come on up, Michael.
Good afternoon, everyone. I'm truly honored and humbled to be here to present some of my PhD work on detecting advanced persistent threat at runtime using host system data provenance. So there's this famous saying in the Unix programming environment from Brian Kernighan and Rob Pike: the power of a system comes from the interactions, the relationships among programs than from the programs themselves. This Unix philosophy has influenced many application and system design, but how is this philosophy connected to our security work here? Let me build this connection by first introducing two important concepts in our work: advanced persistent threat and host system data provenance. What are advanced persistent threats? An advanced persistent threat, or APT, is a targeted attack frequently involving nation-state actors towards government or other large organizations that takes place over a very long time scale. Their goal is usually to gain a control of a specific network of systems, to exfiltrate sensitive data from those networks while remain undetected for an extended period of time. This makes APT fundamentally different from those one-shot conventional attacks. Here is an example of a global APT actor titled APT1 that stole about 6.5 terabytes of data from an organization over the 10 months it persisted in that network. And the longest time where APT1 has this malicious persistence in the victim network is about 4 years and 10 months. So APTs typically follow this kill chain lifecycle model, starting from the initial recon stage, where they identify those valuable targets, maybe like Nokia lab, and initial compromise, such as supply chain compromise or spear phishing, allows the attacker to establish a foothold or a toehold, and then by exploiting the vulnerabilities in the system, they can escalate privileges on the victim systems. They can move laterally throughout the network and slowly exfiltrate confidential information. APT actors leverage a variety of techniques and tactics in each step of the kill chain to launch their APT campaign. And each of these techniques and tactics I show here in this slide, which are only a small subset of all known techniques and tactics, comes in all shapes and sizes, and many of which are zero-day exploits. So when attackers slowly and carefully launch an APT attack, using those techniques and tactics, they leverage information flow between the system entities, such as files and processes, to progressively transition to the next stage in the kill chain. So this kind of a whole system, or even we can consider it whole network style of slow and low attack patterns, make the traditional intrusion detection system inadequate. Because those systems are usually very good at localizing or locating those known attack fingerprints, or they can find the system anomalies, that is a burst of system anomalies, that takes place in a very short period of time. Recognizing the characteristics of APTs, we have shown that whole system data provenance analysis is an effective analytical approach to detecting APTs. So what is data provenance? Data provenance is a chain of records that describe how a piece of data evolves to its present form. Whole system data provenance collects this kind of metadata at the OS level, capturing all system entities such as files, sockets, processes, and activities and interactions among them in a single whole system causality graph representation. The existing capture mechanism typically use a reference monitor-based design that provides strong security and completeness guarantees with respect to information flow capture. Here in the slide, I show one of the designs that leverage Linux security module framework. We can see that the main component that says capture here lives in the kernel space, recording information flows among low-level data objects resulting from the execution of the user-level applications. Then, what are the features of whole system data provenance that make it useful in detecting APTs, and how are these concepts connected to the Unix philosophy here? Well, first, APT kill chain, as we have seen before, consists of a series of steps, each relying on previous step being successful to proceed. Information flows between processes and files in each and across those steps, making them causally related to each other. And this is precisely captured by whole system data provenance in a single causality graph representation as a directed acyclic graph. Although APTs can last for months or even years, meaning that those crucial attack-revealing activities are actually temporally distant from each other, those activities are actually causally close to ensure a successful campaign. Long time scale is one important reason why traditional intrusion detection systems having such a hard time reasoning about those attacks. However, in the causal provenance graph, entities and activities that causally close to each other are actually also close to each other in the provenance graph, facilitating our analysis. So now finally, let's circle back to the whole Unix philosophy. It clearly is the case for APT campaigns, where an APT actors leverage the power of the interaction of programs to deploy their attacks to launch their APT attacks. And our goal is to use whole system data provenance to understand how those interactions deviate from normal system behavior to detect intrusions and to protect our system. This is our approach here. Our approach follows an anomaly detection framework that quantifies intrusion as significant deviations from normality. This means that we have to understand how system behaves under normal conditions before we can do the detection. With whole system data provenance that continuously capture the system execution traces, we formalize our APT intrusion detection problem as a streaming graph analysis problem. Our goal is to train a model of the graph that represents the normal system behavior and use this model to detect intrusions. We perform 4 steps to create such a model in a training stage where we can ensure that our system runs in a safe environment. We first stream the graph into a vertex-centric graph processing framework, where we iterate over each labeled vertex to build an in-memory graph histogram. And each element in the graph histogram represents a unique neighborhood of that vertex. And we're able to efficiently explore the neighborhood of various sizes of each vertex. Periodically, we summarize the histogram into a fixed-sized graph sketch while preserving the similarities among those graph sketches in different time periods. We use locality-sensitive hashing to sketch the graph histogram. We can consider each sketch as a snapshot of the histogram that summarizes the entire history of system execution. To help us focus on important events in each different time periods, we discount the graph histogram elements when they are temporally distant or causally irrelevant in the current time period. And finally, in the last step, we cluster those sketches into a system model. Because our sketches summarizes the system execution as it evolves, our model inherently captures system evolution. We conducted a number of experiments to evaluate our system, and here is a subset of the experimental results using the data set collected from the 2-week-long third adversarial engagement of DARPA's Transparent Computing Program. The provenance data collected here are from 3 different capture systems: Cadets, ClearScope, and Thea. And the average graph size is about 4 million edges. And for each experiment, we train a system model with benign graphs from the data set and test them with benign and attack graph to get false positive and false negative results. We noted that the benign graph in the training and testing do not overlap, so we don't have fake false positive results or false negative results. The table below shows the precision, recall, accuracy, and F-score of the experimental results. As we can see, we obtain really high precision with low false positives and perfect recall with no false negatives. I'm running out of time to actually show the runtime results, but we actually get a fast runtime performance. To conclude, when whole system data provenance provides a holistic view of system execution and understand the whole system execution instead of just a single process is important because it's understanding how programs interacting with each other, how the attackers capture to leverage the power of system interactions to perform attacks. And there are actually many other security and non-security areas that can leverage this rich information source. So I invite all of us to explore a little bit of data provenance, and that concludes my talk. Thank you very much.
So our next speaker is Rami Ali. He's a final year PhD student at Penn State University. He's been an intern with us for 3 summers in a row, so maybe he'll have something more to say to us about the interesting times he's had at Bell Labs once he comes on stage. But his area of research is distributed learning and wireless communications. He's also won several awards, and I think it's on the bio. But I'll invite Rami over to hear more about what he has done in the 3 summers that he spent with us here at Bell Labs.
Thank you. Thank you. Good afternoon, everyone. So I was interning here before 2 times in the mathematics group, and I was doing information theory. This time, I am doing something very different. I am doing deep reinforcement learning. So this is a joint work with Bill Hahn, Ejder, and Bruce, and it uses deep reinforcement learning in routing in large-scale networks. So as we are celebrating Unix today, I wanted to start my talk by talking a little about the Unix philosophy. So the main philosophy of Unix is using a bottom-up approach. So this build complicated things using small things, and then these small modules can work with each other to build something that is complicated by the connectivity of these small modules. So this, along with the paradigm shift from the centralized mainframes into the small decentralized computers, enabled the success of Unix and the use of Unix in large systems, large-scale networking, automation, and a lot of applications. And today, I would like to talk about the most fundamental problem in large-scale networking, which is the packet routing problem in large-scale networks with high dimensional constraints. So this problem is very complicated, as there are many nodes in the network, and the nodes have different requests in terms of the delay rate and so on that lead to a large state space with high dimensional constraints. And in large-scale network, we need to make quick decisions and we need the routing decision to adapt to the network dynamics and make the best out of the network. So there are two classical approaches for tackling this problem. The first approach is distributing the routing decisions, like the BGP protocol. But the problem with this approach is that there is no global view of the network, as the nodes act just using local information. Second classical approach for tackling this problem is using a centralized approach, like the BCE or the Bath computation element. And the problem with this approach is that it is very complex, but the advantage of this approach is having global view of the network. There is someone seeing the whole network and making decision for the whole network. So our approach is sort of an approach between these two approaches. So we would like to decentralize the routing decisions among the node into the networks, but without losing the global view of the network. So our approach is combining between both, so it is still distributed, but we still maintain a global view of the network using a feedback approach that I will explain. So our approach is building a hierarchy into the network first using clustering. So here, for example, this is the first cluster into the network. We are assuming that these three nodes here can communicate with each other easily. The latency between them is small or so, and that form a cluster. And then we can form another cluster using a similar criteria, and these two clusters form the first level of clustering. And then we can cluster these two clusters into a large cluster and get the second level in the hierarchy. And we can continue to do so until we can get this very big cluster at the top level of this. The advantage of this is that we can distribute the routing decision in a straightforward hierarchical fashion, as I will explain. So each of these clusters is assigned a cluster leader. So these yellow nodes here are the cluster leaders, and they take decisions on behalf of the nodes within this cluster. Our approach is using network identifiers. So for example, here, if we look into this node, it is represented by a vector. It is 137, representing how exactly this node is located within the topology. So 1 is saying it is in cluster 1 at the first level of the hierarchy, and then 3 is saying it is in the second level of cluster in cluster 3, and 7 is saying it is part of the very big cluster at the top level of the hierarchy. So let's see how we can distribute the routing decisions using our approach. Our approach is building on the hierarchy and depending on the leader assistance. So for example, here I'm assuming that there is node A represented by this vector 137, and we would like to talk to another node, node B, and this will be with the help of these leaders that I talked about in the last slide. So first, we would like a link connecting these two big clusters, the one on the left and the one on the right. And this is decided by this yellow node here. This is the cluster leaders that will select one of these two links here, the white link or the yellow link. And second, we would like a link connecting between these two small clusters on the left, and we would like another link connecting between these two small clusters on the right, and this is decided also by these two yellow nodes here. These are the cluster leaders. And finally, we can put this route together, so the source will assemble this end-to-end route with the help of these leaders at the different levels. And we can combine this approach with a segment routing approach. So you can think of our approach as incorporating deep reinforcement learning into the segment routing approach. Our approach is maintaining a global view of the network through a source feedback signal. So here, for example, I'm assuming that there are two routes. There is a green route and there is a red route. And I am assuming that the source have used both of this before and likes the green route over the red route. So this signal is sent to the leaders at the different levels, and they take this feedback into account into the next time they get a routing request. The advantage of this is that these nodes don't see the whole network. They just see some local information. So they need to get this feedback to be able to get some sense of the global view of the network. So this group leaders need, this cluster leaders need to make the link selection decision based on a lot of factors, the delay, the jitter, and utilization, a lot of factors. This is a high dimensional problem and needs to be done in real time. So we are approaching this problem using a deep reinforcement learning approach to tackle these challenges. So as we are all aware, deep reinforcement learning is very powerful. The best player in the world in the Go game is a deep reinforcement learning agent invented by DeepMind, but it takes some time to converge, and convergence is not guaranteed. So the classical reinforcement learning approach is the Q-learning approach. And in this approach, the agent or the cluster leader in our case is taking decision based on a table. And this table is updated based on the feedback to make better decision next time. But the problem with this table is that it doesn't scale in large scale networks. So in 2013, deep reinforcement learning started, and deep reinforcement learning replace this table using a neural network. So the neural network in our case takes as an input the state, as utilization, delays, and the network conditions, and then select one of these links, the green link, for example, or this red link based on these conditions. So let's see our approach in group of steps. So first, the cluster leader collects some information about the network. This is local information, utilization, delays, and so on. Based on this, it will select a link for the incoming routing request. And based on how good is this link, it gets some reward saying how good was this link for this routing request. And this experience is stored in an experience replay memory that transfer this reinforcement learning problem into a supervised learning problem. And based on this, this neural network is trained to make better decision next time until we reach an optimal policy, if we reach, because convergence here is not guaranteed. So there are two components of this approach. The first approach is using an experience replay, and here we are building on an approach called the prioritized experience replay, which sample from this memory to train the neural network based on how significant they are. So it doesn't treat all of these samples equally. Second component in our approach is that we are using two neural networks. So the first neural network in the top is the one that make the decision. And second one is giving some feedback for the first one, telling this neural network you are doing well or you are not doing well, and that improves the convergence of the algorithm. Lastly, our approach incorporates a mixed reward signal. So it takes into account the local aspect of the network. So this node making routing decision takes some reward based on how good it is taking decision based on this local information. And also we are taking into account the global aspect of this problem in terms of the global reward. So this global reward is assigned to all nodes in the network, helping the routing decision from node A to node B without distinguishing between them. And this provides the nodes with global view of the network. So let's see an example of our approach applied to very small topology. Here I am assuming that there is source and there is destination, and there are three routes between the source and the destination. The source prefers the red route more than the green route, more than the blue route. So as we see here, the red route is more utilized than the green, than the blue, but there are also some important factors that we consider. First, there shouldn't be any link that is overutilized. So as you see here by this yellow line, this is some threshold. We are telling the nodes in the network, you shouldn't exceed this threshold. And as we see here, the utilization most of the time doesn't go above this threshold. Second aspect of this approach is that we would like to balance the load across these three links. Although the source doesn't prefer this blue link, for example, it's still used from time to time, but not as frequent as the red or the green because the source prefers the red and the green. So our current implementation is using the main platform in deep reinforcement learning, which is the OpenAI platform. But in order for our approach to be evaluated in large-scale network topologies, we would like to replace this network implementation using NS3 network implementation, which will enable evaluation in large-scale network topologies. Our work now is under review, but it is uploaded online on archive, so feel free to read it for more results. And any questions, also, you can email me. Thank you.
Okay, so it is my great pleasure to introduce Aalok Thakkar from the University of Pennsylvania, UPenn, where he is not only studying formal methods for verification and synthesis of computer programs, but is also the chair of operations for the student governments, as well as the president for UPenn's Indian Students Association. And one interesting thing about Aalok is when I talked with him, I asked you guys if you can help me maybe guess, what is the first programming language he programmed in? A hint, Brian Kernighan was talking about it yesterday. Which one was it? I'm surprised nobody else see, right? But that would be too easy. So it was the one that Brian actually is having a little bit of a harder time with, you remember? Haskell, exactly. So that was your first programming language, right? Now don't worry. When he was here in summer, we make him make program Python, so that he learned that as well. Actually, so this was an interesting thing. And then the other interesting nugget that I thought from talking with him was, when I asked Aalok, how would you describe yourself? He said, I think about myself as a logician or mathematician who pretends to be the computer scientist. Well, good luck doing that in front of this audience. All right.
Thank you for that introduction. So today I'll be talking to you about modular program synthesis. Well, Unix was all about solving hard problems, and it was about solving hard problems through design thinking. One of the biggest contributions of Unix is to the design of compilers. Oh, I don't have a clicker. Yes. Back in the 70s, even designing just the front end of a compiler could take weeks or perhaps months. By the way, a compiler is a program which takes a program written in a high-level language like C or Java and turns it into executable code. And a front end of a compiler is a parser. So all that changed with the introduction of Lex and Yak. What these tools do is take the grammar of a language as an input, and they output a parser. And that makes life very easy. It makes writing a parser just a matter of an afternoon. And this approach changed how we go about designing compilers. It made it easy to use the idea of little languages, which is an essential part of Unix. In some sense, Lex and Yak were the first examples of program synthesis. We would like to use program synthesis to solve another challenging problem. The problem that we are looking at is coordinating robots. So here is a fully automated assembly line from Hyundai. There are about a dozen of robots. Each of these robots work independently. They have tens of sensors. These sensors could potentially fail, and they all need to come together to materialize a car. Now, coming up with a protocol, a strategy for all of them to work together is a hard problem, especially a robust strategy which takes care of a number of these parameters. And program synthesis could be very useful here. So program synthesis essentially is a search problem. It's a search problem. You have a bunch of possible transition systems, and you're looking for that one transition system which meets your requirements, which meets your specification. It's not an exaggeration to say that it's actually like finding a needle in a haystack, because when you have, let's say, a transition system on a machine with just 10 states, there could be 10 times 10, 100 possible pairs of states. So there are 100 possible transitions. Every transition system is a subset of these, so there are 2 to the power 100 transition systems at least. If it took me a second to check one transition system, 2 to the power 100 is a couple of trillions of years. So it's impractical. Just exhaustively searching through the space, searching for this needle in the haystack is impractical. We need a systematic approach. One possible way is to convert this problem into propositional logic and use the state-of-the-art SAT solvers to speed up the process. So I'll run through an example to get a feel of things, of how program synthesis, especially for coordination protocols, looks like. So here we have a few of our speakers. Few of the computer scientists go to a hot pot restaurant, but it's a weird restaurant. They only get one chopstick each. And they need to figure out a way to share these chopsticks so that all of them can have a good meal. We are going to use program synthesis to help them enjoy the meal. But as I said, for synthesis, we need a requirement, a set of specifications. So what should the basic specifications be? How would you want your protocol to behave? Feel free to shout out the answers. Are there any requirements that we need to specify first? The obvious one is mutual exclusion. 2 neighbors can't eat at the same time because they're sharing chopsticks. However, if this was the only requirement, what would happen? If we give it to our input tool, come up with a protocol which ensures mutual exclusion, the trivial protocol satisfies it, which is no one eats. We don't want that. We want people to eat. They are hungry. It's almost noon. So we add another condition, which is progress. That is, at every point in time, someone gets to eat. So if these were the 2 requirements, what happens? Any guesses? Well, that's correct. Perhaps 2 people eat, the 3 others starve, and we also don't want that. So we need to change this requirement again to say something like individual progress. That is, everyone who's hungry eventually gets to eat. That is great. We are still missing on something. When we give this as an input, it could potentially generate a protocol where a neighbor could snatch away chopsticks from their neighbors and force them to stop eating. So we add this condition, which is called local actions. That is, the eating or the hungry state of a diner can only be changed by their own actions. So we have 3 great specifications. It's almost a complete specification for this protocol. What happens when I give this as an input? Any guesses? It runs out of memory. The classic problem. So when I actually implemented this in Python, not in Haskell, with 2, 3, and even for 4 diners, we could output a nice protocol. But for 5, it just times out. And we've used state-of-the-art SAT solvers for this. Any guesses where we were going wrong? The encoding itself, the translation from this setting to our Boolean constraints itself introduces exponentially many variables and exponentially many constraints. So that exponential is the core problem. And to tackle that, we had a key insight, which is modularity. The problem is that we are trying to synthesize a protocol for all 5 diners at the same time. Instead, what we could do is look at each individual diner, synthesize protocols for each of them, and find a way to combine these protocols so that we get a protocol for all 5. In context of synthesis, this corresponds to modularity. Modularity, as all of you know, is a well-known concept in programming. It's not very well worked on in synthesis. So we are actually pushing the boundaries of program synthesis. And we did that over last summer at Bell Labs. So what modularity does basically is it constrains the system to look only for those protocols for which you have a modular proof. And that adds a simplification. Our constraints drop from exponential to polynomial, which is a more workable domain. Additionally, it's reasonable to ask for symmetry, which is that the individual protocols of each diner look sort of similar. With symmetry and modularity as 2 more requirements, along with our specifications, we input it to our tool. Our specifications are encoded in linear temporal logic. The tool converts it into Boolean satisfiability, runs a really good SAT solver, outputs a protocol. And when I run it, I get something like this. Someone starts eating. And then people go in a circle, sharing chopsticks. And that's a good enough protocol. Actually, it's a very standard protocol. It's called Peterson's protocol, or a token passing protocol. And we were able to generate this for up to 20 processes in less than 15 minutes. So earlier, we would time out at 5. 4 was the best we could do. Now, we're able to do 20 in just a few minutes. And it's just these two simple insights, modularity and symmetry, which help us do it. Now, 4 to 20 might seem like a very small number. But recall that the total space of solutions is exponential. We have this needle in the haystack idea. So we are actually increasing it by orders of magnitude. And it's still far away from fully automated plants, as you saw. But whatever results that we got just over one summer have convinced us that this is a really promising direction. And one thing is certain, that if we are able to scale it to fully automated assembly lines, modular synthesis, or synthesis in general, will change our entire conception of programming. It'll change how we interact with programs. It'll change how we program. That's it. Thank you.